cadmium. Cadmium is a chemical element with symbol Cd and atomic number 48. This soft, bluish-white metal is chemically similar to the two other stable metals in group 12, zinc and mercury. Like zinc, it demonstrates oxidation state +2 in most of its compounds, and like mercury, it has a lower melting point than the transition metals in groups 3 through 11. Cadmium and its congeners in group 12 are often not considered transition metals, in that they do not have partly filled d or f electron shells in the elemental or common oxidation states. The average concentration of cadmium in Earth's crust is between 0.1 and 0.5 parts per million. It was discovered in 1817 simultaneously by Strohmeyer and Hermann, both in Germany, as an impurity in zinc carbonate. Cadmium occurs as a minor component in most zinc ores and is a byproduct of zinc production. Cadmium was used for a long time as a corrosion-resistant plating on steel, and cadmium compounds are used as red, orange, and yellow pigments, to color glass, and to stabilize plastic. Cadmium use is generally decreasing because it is toxic, and nickel-cadmium batteries have been replaced with nickel metal hydride and lithium-ion batteries. One of its few new uses is cadmium telluride solar panels. Although cadmium has no known biological function in higher organisms, a cadmium-dependent carbonic anhydrase has been found in marine diatoms. Cadmium is a soft, malleable, ductile, bluish-white divalent metal. It is similar in many respects to zinc but forms complex compounds. Unlike most other metals, cadmium is resistant to corrosion and is used as a protective plate on other metals. As a bulk metal, cadmium is insoluble in water and is not flammable. However, in its powdered form it may burn and release toxic fumes. Although cadmium usually has an oxidation state of +2, it also exists in the +1 state. Cadmium and its congeners are not always considered transition metals, in that they do not have partly filled d or f electron shells in the elemental or common oxidation states. Cadmium burns in air to form brown amorphous cadmium oxide. The crystalline form of this compound is a dark red which changes color when heated, similar to zinc oxide. Hydrochloric acid, sulfuric acid, and nitric acid dissolve cadmium by forming cadmium chloride, cadmium sulfate, or cadmium nitrate 2. The oxidation state +1 can be produced by dissolving cadmium in a mixture of cadmium chloride and aluminium chloride, forming the Cd22+ cation, which is similar to the Hg22+ cation in mercury chloride. The structures of many cadmium complexes with nucleobases, amino acids, and vitamins have been determined. Naturally occurring cadmium is composed of 8 isotopes. 2 of them are radioactive, and 3 are expected to decay but have not done so under laboratory conditions. The 2 natural radioactive isotopes are 113Cd and 116Cd. The other 3 are 106Cd, 108Cd, and 114Cd, only lower limits on these half-lives have been determined. At least 3 isotopes 110Cd, 111Cd, and 112Cd are stable. Among the isotopes that do not occur naturally, the most long-lived are 109Cd with a half-life of 462.6 days, and 115Cd with a half-life of 53.46 hours. All of the remaining radioactive isotopes have half-lives of less than 2.5 hours, and the majority have half-lives of less than 5 minutes. Cadmium has 8 known metastates, with the most stable being 113Mcd, 115Mcd, and 117Mcd. The known isotopes of cadmium range in atomic mass from 94.950 U to 131.946 U. For isotopes lighter than 112 U, the primary decay mode is electron capture and the dominant decay product is element 47. Heavier isotopes decay mostly through beta emission producing element 49. One isotope of cadmium, 113Cd, absorbs neutrons with high selectivity, with very high probability. Neutrons with energy below the cadmium cutoff will be absorbed, those higher than the cutoff will be transmitted. The cadmium cutoff is about 0.5 eV, and neutrons below that level are deemed slow neutrons, distinct from intermediate and fast neutrons. Cadmium is created via the S process in low to medium mass stars with masses of 0.6 to 10 solar masses, over thousands of years. In that process, a silver atom captures a neutron and then undergoes beta decay. Cadmium was discovered simultaneously in 1817 by Friedrich Strohmeyer and Carl Samuel Lieberecht Hermann, both in Germany, as an impurity in zinc carbonate. Strohmeyer found the new element as an impurity in zinc carbonate, and, for 100 years, Germany remained the only important producer of the metal. The metal was named after the Latin word for calamine, because it was found in this zinc ore. Strohmeyer noted that some impure samples of calamine changed color when heated but pure calamine did not. He was persistent in studying these results and eventually isolated cadmium metal by roasting and reducing the sulfide. The potential for cadmium yellow as pigment was recognized in the 1840s, but the lack of cadmium limited this application. Even though cadmium and its compounds are toxic in certain forms and concentrations, the British Pharmaceutical Codex from 1907 states that cadmium iodide was used as a medication to treat enlarged joints, scrofulous glands, and chilblains. In 1907, the International Astronomical Union defined the international angstrom in terms of a red cadmium spectral line. This was adopted by the 7th General Conference on Weights and Measures in 1927. In 1960, the definitions of both the meter and angstrom were changed to use krypton. After the industrial-scale production of cadmium started in the 1930s and 1940s, the major application of cadmium was the coating of iron and steel to prevent corrosion. In 1944, 62%, and in 1956, 59% of the cadmium in the United States was used for plating. In 1956, 24% of the cadmium in the United States was used for a second application in red, orange, and yellow pigments from sulfides and selenides of cadmium. The stabilizing effect of cadmium chemicals like the carboxylates cadmium laurate and cadmium stearate on PVC led to an increased use of those compounds in the 1970s and 1980s. The demand for cadmium in pigments, coatings, stabilizers, and alloys declined as a result of environmental and health regulations in the 1980s and 1990s. In 2006, only 7% of total cadmium consumption was used for plating, and only 10% was used for pigments. At the same time, these decreases in consumption were compensated by a growing demand for cadmium for nickel-cadmium batteries, which accounted for 81% of the cadmium consumption in the United States in 2006. Cadmium makes up about 0.1 ppm of Earth's crust. It is much rarer than zinc, which makes up about 65 ppm. No significant deposits of cadmium-containing ores are known. The only cadmium mineral of importance, greenachite, is nearly always associated with sphalerite. This association is caused by geochemical similarity between zinc and cadmium, with no geological process likely to separate them. Thus, cadmium is produced mainly as a byproduct of mining, smelting, and refining sulfidic ores of zinc, and, to a lesser degree, lead and copper. Small amounts of cadmium, about 10% of consumption, are produced from secondary sources, mainly from dust generated by recycling iron and steel scrap. Production in the United States began in 1907, but wide use began after World War I. Metallic cadmium can be found in the Vilya River Basin in Siberia. Rocks mined for phosphate fertilizers contain varying amounts of cadmium, resulting in a cadmium concentration of as much as 300 mg/kg in the fertilizers and a high cadmium content in agricultural soils. Coal can contain significant amounts of cadmium, which ends up mostly in flue dust. Cadmium in soil can be absorbed by crops such as rice. Chinese Ministry of Agriculture measured in 2002 that 28% of rice it sampled had excess lead and 10% had excess cadmium above limits defined by law. Some plants such as willow trees and poplars have been found to clean both lead and cadmium from soil. Typical background concentrations of cadmium do not exceed 5 Ng/m3 in the atmosphere, 2 mg/kg in soil, 1 μg/L in fresh water and 50 Ng/L in seawater. The British Geological Survey reports that in 2001, China was the top producer of cadmium with almost 1/6 of the world's production, closely followed by South Korea and Japan. Cadmium is a common impurity in zinc ores, and it is most often isolated during the production of zinc. Some zinc ores concentrates from sulfidic zinc ores contain up to 1.4% of cadmium. In the 1970s, the output of cadmium was 6.5 pounds per ton of zinc. Zinc sulfide ores are roasted in the presence of oxygen, converting the zinc sulfide to the oxide. Zinc metal is produced either by smelting the oxide with carbon or by electrolysis in sulfuric acid. Cadmium is isolated from the zinc metal by vacuum distillation if the zinc is smelted, or cadmium sulfate is precipitated from the electrolysis solution. History of the world production of cadmium. Cadmium output in 2005. Cadmium is a common component of electric batteries, pigments, coatings, and electroplating. In 2009, 86% of cadmium was used in batteries, predominantly in rechargeable nickel-cadmium batteries. Nickel-cadmium cells have a nominal cell potential of 1.2 V. The cell consists of a positive nickel hydroxide electrode and a negative cadmium electrode plate separated by an alkaline electrolyte. The European Union put a limit on cadmium in electronics in 2004 of 0.01%, with some exceptions, and reduced the limit on cadmium content to 0.002%. Another type of battery based on cadmium is the silver-cadmium battery. Cadmium electroplating, consuming 6% of the global production, is used in the aircraft industry to reduce corrosion of steel components. This coating is passivated by chromate salts. A limitation of cadmium plating is hydrogen embrittlement of high-strength steels from the electroplating process. Therefore, steel parts heat-treated to tensile strength above 1300 MPa should be coated by an alternative method. Titanium embrittlement from cadmium-plated tool residues resulted in banishment of those tools in the A-12/SR-71, U-2, and subsequent aircraft programs that use titanium. Cadmium is used in the control rods of nuclear reactors, acting as a very effective neutron poison to control neutron flux in nuclear fission. When cadmium rods are inserted in the core of a nuclear reactor, cadmium absorbs neutrons, preventing them from creating additional fission events, thus controlling the amount of reactivity. The pressurized water reactor designed by Westinghouse Electric Company uses an alloy consisting of 80% silver, 15% indium, and 5% cadmium. QLED TVs have been starting to include cadmium in construction. Some companies have been looking to reduce the environmental impact of human exposure and pollution of the material in televisions during production. Cadmium oxide was used in black and white television phosphors and in the blue and green phosphors of color television cathode ray tubes. Cadmium sulfide is used as a photoconductive surface coating for photocopier drums. Various cadmium salts are used in paint pigments, with CDs as a yellow pigment being the most common. Cadmium selenide is a red pigment, commonly called cadmium red. To painters who work with the pigment, cadmium provides the most brilliant and durable yellows, oranges, and reds, so much so that during production, these colors are significantly toned down before they are ground with oils and binders or blended into watercolors, gouaches, acrylics, and other paint and pigment formulations. Because these pigments are potentially toxic, users should use a barrier cream on the hands to prevent absorption through the skin, even though the amount of cadmium absorbed into the body through the skin is reported to be less than 1%. In PVC, cadmium was used as heat, light, and weathering stabilizers. Currently, cadmium stabilizers have been completely replaced with barium zinc, calcium zinc, and organotin stabilizers. Cadmium is used in many kinds of solder and bearing alloys, because it has a low coefficient of friction and fatigue resistance. It is also found in some of the lowest melting alloys, such as woods metal. Helium-cadmium lasers are a common source of blue ultraviolet laser light. They operate at either 325 or 422 nm in fluorescence microscopes and various laboratory experiments. Cadmium selenide quantum dots emit bright luminescence under UV excitation. The color of this luminescence can be green, yellow or red depending on the particle size. Colloidal solutions of those particles are used for imaging of biological tissues and solutions with a fluorescence microscope. Cadmium is a component of some compound semiconductors, such as cadmium sulfide, cadmium selenide, and cadmium telluride, used for light detection and solar cells. HGCDTE is sensitive to infrared light and can be used as an infrared detector, motion detector, or switch in remote control devices. In molecular biology, cadmium is used to block voltage-dependent calcium channels from fluxing calcium ions, as well as in hypoxia research to stimulate proteasome-dependent degradation of HIF-1-alpha. Cadmium selective sensors based on the fluorophorobotopy have been developed for imaging and sensing of cadmium in cells. One of the most popular way to monitor cadmium in aqueous environments is the use of electrochemistry. One example is by attaching a self-assembled monolayer that can help obtain a cadmium selective electrode with a PPT level sensitivity. Cadmium has no known function in higher organisms, but a cadmium-dependent carbonic anhydrase has been found in some marine diatoms. The diatoms live in environments with very low zinc concentrations, and cadmium performs the function normally carried out by zinc and other anhydrases. This was discovered with X-ray absorption fluorescence spectroscopy. The highest concentration of cadmium is absorbed in the kidneys of humans, and up to about 30 mg of cadmium is commonly inhaled throughout human childhood and adolescence. Cadmium is under preliminary research for its toxicity in humans, potentially affecting mechanisms and risks of cancer, cardiovascular disease, and osteoporosis. The biogeochemistry of cadmium and its release to the environment has been the subject of review, as has the speciation of cadmium in the environment. Individuals and organizations have been reviewing cadmium's bioinorganic aspects for its toxicity. The most dangerous form of occupational exposure to cadmium is inhalation of fine dust and fumes, or ingestion of highly soluble cadmium compounds. Inhalation of cadmium fumes can result initially in metal fume fever but may progress to chemical pneumonitis, pulmonary edema, and death. Cadmium is also an environmental hazard. Human exposure is primarily from fossil fuel combustion, phosphate fertilizers, natural sources, iron and steel production, cement production and related activities, non-ferrous metals production, and municipal solid waste incineration. Bread, root crops, and vegetables also contribute to the cadmium in modern populations. There have been a few instances of general population poisoning as the result of long-term exposure to cadmium in contaminated food and water, and research into an estrogen mimicry that may induce breast cancer is ongoing. In the decades leading up to World War II, mining operations contaminated the Jins River in Japan with cadmium and traces of other toxic metals. As a consequence, cadmium accumulated in the rice crops along the riverbanks downstream of the mines. Some members of the local agricultural communities consumed the contaminated rice and developed atai disease and renal abnormalities, including proteinuria and glucosuria. The victims of this poisoning were almost exclusively postmenopausal women with low iron and other mineral body stores. Similar general population cadmium exposures in other parts of the world have not resulted in the same health problems because the populations maintain sufficient iron and other mineral levels. Thus, although cadmium is a major factor in the atai disease in Japan, most researchers have concluded that it was one of several factors. Cadmium is one of 6 substances banned by the European Union's Restriction on Hazardous Substances Directive, which regulates hazardous substances in electrical and electronic equipment but allows for certain exemptions and exclusions from the scope of the law. The International Agency for Research on Cancer has classified cadmium and cadmium compounds as carcinogenic to humans. Although occupational exposure to cadmium is linked to lung and prostate cancer, there is still a substantial controversy about the carcinogenicity of cadmium in low environmental exposure. Recent data from epidemiological studies suggest that intake of cadmium through diet associates to higher risk of endometrial, breast and prostate cancer as well as to osteoporosis in humans. A recent study has demonstrated that endometrial tissue is characterized by higher levels of cadmium in current and former smoking females. Cadmium exposure is a risk factor associated with a large number of illnesses including kidney disease, early atherosclerosis, hypertension, and cardiovascular diseases. Although studies show a significant correlation between cadmium exposure and occurrence of disease in human populations, a necessary molecular mechanism has not been identified. One hypothesis holds that cadmium is an endocrine disruptor, and some experimental studies have shown that it can interact with different hormonal signaling pathways. For example, cadmium can bind to the estrogen receptor alpha, and affect signal transduction along the estrogen and MAPK signaling pathways at low doses. The tobacco plant readily absorbs and accumulates heavy metals, such as cadmium, from the surrounding soil into its leaves. These are readily absorbed into the user's body following smoke inhalation. Tobacco smoking is the most important single source of cadmium exposure in the general population. An estimated 10% of the cadmium content of a cigarette is inhaled through smoking. Absorption of cadmium through the lungs is more effective than through the gut, and as much as 50% of the cadmium inhaled in cigarette smoke may be absorbed. On average, cadmium concentrations in the blood of smokers is 4 times 5 times greater, and in the kidney, 2-3 times greater than non-smokers. Despite the high cadmium content in cigarette smoke, there seems to be little exposure to cadmium from passive smoking. In a non-smoking population, food is the greatest source of exposure. High quantities of cadmium can be found in crustaceans, mollusks, offal, and algae products. However, grains, vegetables, and starchy roots and tubers are consumed in much greater quantity in the U.S., and are the source of the greatest dietary exposure. Most plants bioaccumulate metal toxins like CD, and when composted to form organic fertilizers yield a product which can often contain high amounts of metal toxins for every kilo of fertilizer. Fertilizers made from animal dung or urban waste can contain similar amounts of CD. The CD added to the soil from fertilizers become bioavailable and toxic only if the soil pH is low. Zinc is chemically similar to cadmium, and some evidence indicates the presence of Zn ions reduces cadmium toxicity. Zinc, Cu, Ca, and Fe ions, and selenium with vitamin C are used to treat CD intoxication, though it is not easily reversed. Because of the adverse effects of cadmium on the environment and human health, the supply and use of cadmium is restricted in Europe under the REACH regulation. The EFSA panel on contaminants in the food chain specifies that 2.5 μg/kg body weight is a tolerable weekly intake for humans. The joint FAO/WHO Expert Committee on Food Additives has declared 7 μg/kg BW to be the provisional tolerable weekly intake level. The U.S. Occupational Safety and Health Administration has set the permissible exposure limit for cadmium at a time-weighted average of 0.005 ppm. The National Institute for Occupational Safety and Health has not set a recommended exposure limit and has designated cadmium as a known human carcinogen. The IDLH level for cadmium is 9 mg/m3. In May 2006, a sale of the seats from Arsenal F.CS Old Stadium, Highbury in London, England was cancelled when the seats were discovered to contain trace amounts of cadmium. Reports of high levels of cadmium use in children's jewelry in 2010 led to a U.S. Consumer Product Safety Commission investigation. The U.S. CPSC issued specific recall notices for cadmium content in jewelry sold by Claire's and Walmart stores. In June 2010, McDonald's voluntarily recalled more than 12 million promotional Shrek Forever After 3D collectible drinking glasses because of the cadmium levels in paint pigments on the glassware. The glasses were manufactured by Arc International, of Millville, New Jersey, USA.